Okay, so what I want to do is collect a few more facts, theorems, about eigenvalues related to other stuff like similarity, like the characteristic polynomial, like many more things, but the main theme is still going to be those eigenvalues. So remember that we've seen, so here's a reminder. This marker is not that good. So reminder, similar matrices have the same, what? The same trace, right? The same determinant. Same rank. In fact, I think these are the three things that we've stated so far. What I want to prove now, that similar matrices also have the same characteristic polynomial. So this is going to be our first theorem, and we're going to prove it. It's not a difficult proof. Similar matrices have the same characteristic polynomial. Polynomial. And if they have the same characteristic polynomial, that implies automatically that they have the same roots of that polynomial, which are the eigenvalues. And eigenvalues. Values. So do you agree that it suffices to prove that they have the same polynomial? Right? This follows automatically. Okay, so let's prove it. Here's the proof. And recall that we've seen in an example matrices that have the same characteristic polynomial in eigenvalues, but are not similar, right? That was those 3×3a and 3×3b that we did as examples previously. So this is still not an if and only if statement. Okay, so here's the proof. So the data is that A and B are similar, right? Take two similar matrices. This implies, by the definition or by a theorem that says that it's an equivalent definition, that there's an invertible matrix P such that, which one? A equals P inverse BP. Do you agree? Okay. And P is invertible. So that's by definition. Therefore, let's compare their characteristic polynomials. Here's the characteristic polynomial of A. Do you agree? Right? The characteristic polynomial is the determinant of A minus alpha I. This turns out to be a polynomial in alpha, right? So let's use the fact that A can be written as P inverse BP. So I can write this as the determinant of P inverse BP minus alpha I. Right? And now I'm going to throw in P and P inverse and let them appear here on both sides of I. I can do that because P inverse times P is the identity. Right? So it does nothing. So this is the same as P inverse BP minus alpha P inverse I P. Do you agree that this is just I? Good. And now I can distribute, right? Now I can pull out, so everything is still living inside the determinant, but now I can pull out a P inverse as a factor from, I can first throw the alpha inside here, because it's a scalar, it can move freely. among the multiplication. And then I can pull out a P inverse from the left. And then I have B minus alpha I. And then I have P. Right? So matrix multiplication satisfies this distributivity with respect to addition. Good? Okay. Now I'm going to use a property that we know of the determinant. That the determinant of a product is the same as the product of the determinants. So I have the determinant of P inverse times the determinant of B minus alpha I times the determinant of P. Right? And furthermore, what is the determinant of P inverse? 1 over the determinant of P. So I have 1 over the determinant of P times the determinant of B minus alpha I times the determinant of P. Do you agree? So I'm not writing down all the justifications for each step, but I said them. Okay? Of course, if you want to write something like this formally, you need to write down every justification for every single move. Okay? And once I have these are numbers. Determinants are just numbers. I can commute, right? So this and this cancel, and I get that this equals the determinant of B minus alpha I, which is the characteristic polynomial of B. Good? So that wraps up the proof. Rather straightforward, I would say. Questions? Okay. So let's just write as a remark that all the shared properties that we mentioned are not sufficient to prove similarity. So all the shared properties mentioned so far, and there are more, so namely the trace, the determinant, the rank, the characteristic polynomial, and the eigenvalues are not sufficient conditions for similarity. Okay, they're necessary conditions. Similar matrices have them, but they're not sufficient. Okay, even if two matrices share all these properties, they're not necessarily similar. I can give you maybe as an exercise, show that if you take a matrix, a square matrix A, and take its transpose, so it's a square matrix, so its transposes of the same dimension, A and A transpose have the same characteristic polynomial. Okay, and therefore the same eigenvalues. Okay, always. This is rather easy. Okay, think of how you show it. The first thing you have to observe is that they have the same determinant. That we know. I think we mentioned that. Okay, so but they don't necessarily have the same eigenvectors. Okay, the eigenvectors are solutions to systems of equations, and when you transpose, it completely changes the system, right? Okay, so okay, so I guess this wraps up this statement. Let's move on to the next statement relating to that I want to connect to eigenvalues. And again, a question? Yeah.
On the excerpt, what do we know about them? Only that they're invertible? That's it?
No, they're not invertible.
Oh, they're not?
No, there's no statement about invertibility. I'm taking a square matrix and its transpose. That's all. Okay? Okay. So I'm going to start with a reminder. So recall that if we take a square matrix, let's emphasize that it's a square matrix, n by n. is invertible, now I'm using the invertibility property of a matrix, which a priori has nothing to do with being similar or not. It's a completely different notion. Okay, so an by n is invertible if and only if, and in fact there are going to be like 10 if and only if nows, if and only ifs now. So what do we have? We have the determinant of A is non-zero, right? If and only if we had that the rank of A is full, n, right? If and only if A's canonical form is what? Is I. So when you do row operations all the way to the reduced echelon form, the canonical form, you get to I. Okay. If and only if, what else do we have here? For every B vector in Fn, where F is the field, there is a unique solution, to the system Ax equals B. Remember these? Okay. If and only if, I ran out of board. That's because I only used half of it. Duh. The rows of A are linearly independent, right? That's equivalent to saying that it has full rank. So there are many ways of stating these, right? The rows of A are linearly independent. If and only if
dimension of the cross space.
Let's continue here. If and only if, it's just continuing the list, if and only if A represents an invertible linear map, linear operator, right? So if you define T of V to be AV, then T is going to be invertible, right? And the linear map is going to be a linear operator, right? Because it's a square matrix, so it's going to go from Fn to Fn, for example. Okay, so it's a linear operator, and for a linear operator where the domain and range are the same, in particular their dimensions are the same, and if the dimension of the domain and range of a linear operator are the same, then being invertible is the same as being one-to-one, right? And onto, but for every function, if it's one-to-one and onto, it's invertible. But if it's a linear map from V to V, then it suffices for it to be one-to-one, it's going to be invertible. Because it's one-to-one if and only if it's onto. Remember that theorem? Remember that? If the dimension of V1 equals the dimension of V2, and T is a map between them, then it's one-to-one if and only if it's onto. So it's the same as saying that an invertible linear map T, let's call it, and A represents a one-to-one map T, right? And if T is a one-to-one map, what is that equivalent to? Well, right, but that's not saying much because that's hidden in here, but something that sounds completely different.
The kernel is 0.
Right, the kernel is 0. And the kernel of T and the kernel of A are the same thing, right? So the kernel of A or the null space, right? The kernel of A is 0, right? Do you agree that just using the words, the terminology, we can basically continue this list for another 3 boards? Okay, good. I want to add 2 more new ones that haven't been up here yet. So let's stop the existing list and add 2 new ones. All of these we already know. All of these are facts that stem from stuff that we did. Okay. So the first new one is 0 is not an eigenvalue of A. Of A or of the t it represents, same thing. Okay, we'll prove this in a minute. And another one, if and only if the free coefficient of the characteristic polynomial of A is not 0. Okay, so these are the 2 new facts that are related to our topic, our current topic of eigenvalues and the characteristic polynomial. Okay, so I'm going to forget everything in the middle, and I want to prove these 2 are related to invertibility. And in order to do so, I can show that each of them is an if and only if with any one of these properties, because they're all equivalent. Okay, so let's prove. Let's call this 1, and let's call this 2. And these are the 2 that I want to prove right now. Okay, so here goes. Okay, so let's prove 1. Proof of 1. So take a deep breath. It's going to be a bit long. Okay, so 0 is not an eigenvalue. 0 is not an eigenvalue, is not an eigenvalue, means if and only if the determinant, or let's say it differently, 0 is an eigenvalue. 0 is an eigenvalue if the determinant of A minus 0I is 0. That's what it means to be an eigenvalue, right? That the determinant of A minus alpha I with that alpha is 0, that it's a root of this characteristic polynomial. Do you agree? Good? So 0 is an eigenvalue if and only if this determinant is 0, but subtracting 0I is not doing much, so that's if and only if the determinant of A is 0. And that's it, we're done. Told you it was long. Good? If the determinant is 0, then 0 is an eigenvalue. So if the determinant is not 0, which is equivalent to invertibility, then 0 is not an eigenvalue. Good? Okay, so that's the proof of 1, and the proof of 2, which is going to be just as long. Everybody good? Okay. Proof of 2, remember that 2 said that the free coefficient of the characteristic polynomial is not 0. So let's write the characteristic polynomial. Let P of x be a n x to the power n plus a n minus 1 x to the n minus 1 plus dot 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 plus a1x plus a0. Okay? Let this be the characteristic polynomial. The free coefficient is this little alpha 0 here, right? So if alpha 0 is 0, that's if and only if alpha 0 is 0, then I can eliminate it. And then 0 is a root, right? 0 is a root of any polynomial with no free coefficient. It annihilates it. Do you agree? Okay? That's if and only if 0 is a root of the characteristic polynomial, which is what? 0 is a root of p of x, meaning that 0 is an eigenvalue. Do you agree? But if 0 is an eigenvalue, then A is not invertible. Okay? So that's it. Good? Okay. So these are two more properties that are equivalent to being invertible. And honestly, this list seems like too long to memorize, and that's not the point. You're not supposed to memorize the entire list. You're really supposed to kind of start getting the feeling, start getting used to these facts being the same as you do more and more practice, more and more exercises. You start thinking, oh, A, the determinant is 0, A is not invertible. You just start thinking it, okay? You see them as the same thing, okay? And you don't have to really memorize a list of 20 different equivalent statements, each of which is in terms of a totally different property or definition. Or you just, as you practice, start getting the hang of it. Okay, so that's always the best approach, not to memorize a list and then approach the homework or whatever questions you're practicing with. Rather, do the questions and gradually, with open notes, and gradually start just getting used to these statements being different ways of looking at the same thing. Okay, good?
Can I ask on proof of 1?
Yeah.
I get the direction from the determinant of A gets us to the line above. I don't get from, how did you say that 0 is an eigenvalue, that A minus...
This is the characteristic polynomial,
Yeah.
right?
Yeah.
Saying that the characteristic polynomial is when there's an alpha here. Alpha is an eigenvalue if it's a root of the characteristic polynomial. If when you plug it in, you get 0. Okay, you're still looking at this and not seeing a polynomial. That's the problem. This is a polynomial in alpha evaluated at 0. Good? Sure?
Yeah, I got it.
Okay. Okay. Wonderful. So this is yet again another fact. And let's continue that. Wait, something got messed up here. There we go. Okay, so the next fact that I want to show is that, show and prove, in fact, I want to prove that AB and BA have the same eigenvalues. Which is, again, a useful little theorem. So theorem, AB and BA have the same eigenvalues. And for A, B, and BA, we also know other shared properties, right? They're not equal. Matrix multiplication is not commutative. AB is not equal to BA. Maybe let's write this. Note that AB is not equal to BA in general, right? That's rarely the case. But what properties do they have in common always that we've seen already? Right, they have the same determinant. The same rank? Nope. Right? One can be 0 and the other can be, right? So AB is not equal to BA in general. They do have the same determinant. And the same trace. We proved that the trace of AB and the trace of BA are the same. Remember that? The same determinant and trace, but not rank. In general. Okay? Do you understand why saying that they have the same rank is unlikely? Okay? You can take A and B, multiply them, and get the 0 matrix, right? The matrices with the operation of multiplication has what we call 0 divisors, right? You can take two non-zero matrices, multiply them, and get the 0 matrix. Okay, so the rank of the product would be 0, whereas if you multiply them the other way, you'd get a non-zero matrix, so automatically it won't have a 0 rank. Okay?
But if they both don't have full rank, if one don't have the full rank?
Okay, so we can take this in various directions. That would be very good exercises, but not right now. Right now, I want to prove this, that they have the same eigenvalues. Okay? Okay, so this is just a little side discussion. Let's prove the theorem. Proof. And the proof is going to be a bit different than proofs we've seen, at least right now. So what I'm going to do is let V be a non-zero vector, be an eigenvector, corresponding to alpha 0 to an eigenvalue alpha 0 of AB. So what I want to show is that they have the same eigenvalues. Okay? So I'm going to take an eigenvalue of AB. I want to show that alpha 0 is an eigenvalue of BA. Good? So I'm taking an eigenvalue of AB, and I'm taking a corresponding eigenvector. Okay? So what I get, therefore, what does it mean? It means that if we take AB times V, we get alpha 0 times V. That's what it means to be an eigenvector and an eigenvalue. Do you agree? Good, everybody? Okay. Now, what are we looking for? We're looking for some W. It's not necessarily going to be V. Some W such that BA times W is alpha 0 W. Right? So let's write that. Let's erase here maybe. So we know that ABV equals alpha 0 V. This I just copied from the previous board. We're looking for some W such that BA times W equals alpha 0 W. Right? That would mean that alpha 0 is an eigenvalue of BA as well with that eigenvector W. Good? Okay. So it's kind of a good guess to take W to be B times V. Okay? Take W to be B times V. Why? Because A times B times V is alpha 0 times V, right? Then, what is BAW? It's BA BV, right? ABV is alpha 0 V, right? So it's B times ABV alpha 0 V, right? And alpha 0 is a scalar. It can hop here, so it's alpha 0 BV, which is alpha 0 W. BV was W. Do you agree? So if we take W to just be BV, then BAW is alpha 0 W. Good? Are we done? Seems like we're done. Why am I asking? We're probably not done. Think. What's missing? Something is still missing.
Maybe alpha is 0.
Well, there's no restriction for the eigenvalue to be 0, right? But you're close. What cannot be 0?
W.
W, right? So we're looking for W which is not 0 such that this holds. Do you agree? Do you agree?
Yeah.
Okay. So we have to show that what we found is indeed a non-zero vector. Okay. So so we're looking for W not 0 such that pa-pam, pa-pam, pa-pam. Okay. So we still need to show this. We didn't show that this W is indeed non-zero. So if W equals BV equals 0, right? W was BV. That's the W that we took. If W equals 0, then what can we say? Then BV equals 0. And then we go up here, then ABV equals A times 0, which is 0, right? But ABV is alpha 0 V, right? Equals alpha 0 V. Do you agree? So can that be? Is there any conflict here? Is there any contradiction here?
Yeah.
So we know that V is not 0. That's where we started.
Alpha is 0.
So if alpha 0 V is 0, this forces alpha 0 to be 0. Do you agree? Okay. And then there's no contradiction. Okay. So something is wrong. We're looking for a non-zero W such that all of this happens. But W could be 0 and nothing goes wrong, so we didn't prove anything, right? We need to find a non-zero. So what do we do? The problem is that alpha 0 could be 0, right? And that is completely legitimate. Okay? So what we do, as we often do in many, many proofs in mathematics, we set aside a specific case which gives us a headache and deal with it separately. Right? So we go back to the beginning of the proof. Therefore, we got here. So let's add here, or for the very beginning, let's go back to this board. Let V0, V be a non-zero eigenvector corresponding to an eigenvalue alpha 0, and assume that alpha 0 is not 0. Okay. Assume alpha 0 is not 0. I'm adding an assumption here. Okay? And I'm going to deal separately with the situation where alpha 0 is 0. Okay? So assume that alpha 0 is not 0, and I'm back to this board, and we're looking for W, a non-zero vector such that if W equals BV equals 0, then we agree that that forces alpha 0 to be 0, and now it's a contradiction, because we're assuming that alpha 0 is not 0. Okay? In contradiction to the assumption that alpha 0 is not 0. Okay? So when alpha 0 is not 0, W is not 0. Because if it were, it forces alpha 0 to be 0. Right? Okay. But now we have to handle separately the situation where alpha 0 is 0. And we put a line, trace back to the start, and start from scratch. Assume alpha 0 is 0. If alpha 0 equals 0, is an eigenvalue of AB, then what does it mean? What does it mean? It means that the determinant of AB minus 0i is 0, right? Therefore, the determinant of AB, let's write it, AB minus 0i is 0, right? That's what it means for 0 to be an eigenvalue. Therefore, the determinant of AB is 0. Therefore, the determinant of BA is 0, right? Because the determinant is invariant under multiplication, because basically this is the determinant of A times the determinant of B, and then they're numbers and we can commute them. Okay? And therefore, if the determinant of BA is 0, then the determinant of BA minus 0i is 0, which means that 0 is an eigenvalue of BA. And now the proof is complete. Good? Now, if you would open a book and look for this proof, you would probably see it in the following way. Assume first that alpha 0 is 0. Then, now assume that alpha 0 is not 0, and then you get all this. Okay? So the reason I did it the other way around is to show where it stems from. Why do I separate this case? Okay, and usually when you prove things on your own, you don't know how to start, right? And where to say, okay, let's first consider this case and then consider this case. Rarely do you know how to get started. You start doing stuff and see where it leads you, right? But it's important to pay attention to little details like things like this. If you want something to be an eigenvector, it has to be non-zero. Okay? 0 is always an element in the kernel of A minus alpha I, right? But it's not an interesting one, right? It's not going to be an eigenvector. Okay? TV equals alpha V always holds for V equals 0, right? But you can't form a basis using it. Therefore, it doesn't do what we want it to do. Good? Just like in anything you do, you have to pay attention. If you're dividing by something, that something may be 0, you have to deal with it separately. Okay, same idea. Everybody good? Okay, wonderful. We're not done. One more statement concerning, lost it. There it is. One more statement concerning eigenvalues. So remember that not every matrix is diagonalizable, right? The situation where a matrix is diagonalizable depends on whether, we had several criteria. For example, if it represents a diagonalizable T, meaning that T has an a basis, that V has a basis of eigenvectors of T, right? Or another way of saying the same thing is that a matrix is diagonalizable if it's similar to a diagonal matrix. If there's a P, an invertible P, such that P inverse AP equals a diagonal matrix, right? If and only if for every eigenvalue, the multiplicities agree. The algebraic multiplicity equals the geometric multiplicity, right? We had various ways of saying, but that's not always the case. We saw an example of a matrix that's not diagonalizable. We even saw more than one. We saw an example where the alphas didn't all have the same multiplicities, and we saw examples where the alphas were just not in the field, right? Okay, so what do we do? So not every A is diagonalizable. Right? So when it's not, it means it doesn't have a diagonal form. We really want diagonal forms because they're easy to work with, and we'll see a bit more on that a bit later. So what do we do? The entire process that we had so far fails. Okay? It's not going to have a diagonal form. Okay? What do we do? So there are theorems. There's a vast theory that extends beyond diagonalization, giving forms that are not diagonal, but almost diagonal. A bit of here and there non-zero entries off the diagonal. Okay? We're not going to go in detail into those theories. I'm just going to mention one or two. Just mention them. So you know that they exist, and if you ever need them, you can look them up. Okay? Some more advanced courses go into details of other forms of matrices that are not diagonal but are useful. Okay, so here's one. So a more general theorem says, a more general theorem states that if you are working over a field which is called algebraically closed, it includes the roots of any polynomial. Okay? That if f is algebraically, I think that's how you spell it. You can check. Closed, or is it just algebraically? Is this correct? Okay. If f is algebraically closed, for example, C. C is algebraically closed. Any polynomial in C, all its roots are in C. R is not algebraically closed. The polynomial x squared plus 1 doesn't have roots in R. Right? Okay, so do you...
Another example other than C, because C is kind of like the obvious example.
C is... Right, C... we don't know many more fields.
Yeah,
do you have any other examples of fields other than R and C?
Well,
right?
no,
There's Q.
Q
Q is not algebraically closed as well. But in order to give you more examples of algebraically closed fields, you first have to know more fields. Okay? And we didn't go very deep into that theory at all. We mentioned that there are those things called finite fields. Remember? And we didn't do much with them. We just mentioned their existence. And that's basically where we stopped. Okay? So I'm not going to go into these details here. For us, the algebraically closed field in this course is C, whereas R and Q are not. Okay? But if it's a good field in that sense, contains the roots of all the polynomials, then every matrix is similar to a matrix of the form so here's a matrix of the form. It's going to have entries along the diagonal. These entries are what we have in a diagonal matrix as well, right? It's going to have zeros off the diagonal. So if I would stop here, it would be just a diagonal matrix. But it's also going to have a few ones, okay? And the ones are only going to live above the main diagonal in some of the entries. So there may be a few ones. Maybe here there's going to be a 1, and here there's going to be a 1. Here maybe there's a 0, and another 0, and here a 1 again. So there can only be ones along not the main diagonal, I don't know what it's called, maybe the semi-diagonal, or the diagonal above the main diagonal, and that's it. Okay? So this is pretty good, pretty close to being completely happy, right? Pretty close. And that's guaranteed over any algebraically closed field. Did I spell this correctly? Okay? So if you're working over the complex numbers, this is guaranteed. If you're working over R, it's not. We still need to pay even a bigger price in order to say every matrix. Okay? So we'll say that in a minute. This is called the Jordan form, or Jordan canonical form, or Jordan normal form. Has various names. So we'll just call it the Jordan normal form. It's also called Jordan canonical form. Okay? So basically what it is, I can tell you even what it is. It's not a mystery. Okay? It's not a mystery. What it is comprised of diagonal blocks So the diagonal is kind of made up of little blocks. So here's an example of a block. And here's maybe another block. This is not written well. Here's another block. This is a 1-by-1 block. Okay, and here maybe there's another block. Okay, so the diagonal is, the matrix is diagonal blocks, and everything outside those blocks is zeros. Okay, and each block is of the form some eigenvalue on the diagonal with its multiplicity. So the same alpha may be 3 times, and then ones on the diagonal above it. So this is called a Jordan block. Okay, and it's this little blocks that sit along the diagonal. If alpha has a multiplicity 1, then it's just going to look like this. It's going to be a 1-by-1 block with no ones. Okay, so that's...
Like, it's all the same alpha. Not
in a block, it's all the same alpha. On the different blocks, it's the different alphas. Okay? And in particular, if all the alphas have multiplicity 1, then we're back at good old diagonal form, right? Because all the blocks are 1-by-1, and these ones don't exist. Okay? So I'm not going to go into how you prove this. This is way beyond the scope of this course, but just so you know that this exists. Okay? And I'm just going to mention in saying there are even more general theorems that say that above any field, every matrix is similar to what's called Frobenius canonical form, or it's also called a rational canonical form, and I'm not even going to mention what it is. Okay, it has more off-diagonal non-zero entries, and so things exist. Okay, the theory exists. Okay, just to mention. Okay. Okay. Back to
When you said a Jordan normal form, is that a 3 by 3 or just an?
No. This is of the form. I said it could be a 1 by 1. It could be 2 by 2. Okay, depends on the multiplicity of that specific eigenvalue.
If there's a theorem to the size of it
According to the multiplicity of alpha as an eigenvalue. Okay. Okay. This is really just kind of, it's a bit off track for this course, okay? It's just for your general knowledge, this specific board, okay? One other statement of this, of kind of the same spirit that I want to mention, again, without proof, but that is going to lead us to something that is something we want to know and is very useful. Is the following. So, again, without proof, so here's another theorem. If all eigenvalues of A belong to F, so for example, the eigenvalues are the roots of the characteristic polynomial, right? If they all sit in the field F, that doesn't necessarily mean that F is algebraically closed, okay? It's per matrix. If that specific matrix, all its entries belong to F, okay? If F is algebraically closed, then for any matrix, all the eigenvalues are going to belong to that F, right? But if it's not algebraically closed, for some matrices, all the eigenvalues are going to be in the field, and for others, not. Okay? So if you're looking at a matrix such that all the eigenvalues belong to F, then A is similar to a triangular matrix of the form so we're still going to have the alphas along the diagonal. These are the eigenvalues of A. We're still going to have a big zero under the diagonal, but we're going to have stuff above the diagonal, and I can't say much about it. So this theorem is a weaker theorem in terms of the result. Here there can be anything non-zero. Okay? So it's a weaker theorem. It doesn't give us what we really want. It only makes the bottom half zero, but up here we can still have various entries. Okay, but it's still something. Okay? And it's true for any A as long as all the alphas are in the field. Okay, where alpha i's are the eigenvalues. Okay? But there's a nice result stemming from this, a corollary. Corollary. Suppose that A satisfies this, that all the eigenvalues belong to F. So for such A, the claim is that the determinant of A equals the product, do you know the notation big pi? Product? Let's make it a big pi. Product of the alpha i's. Okay, this stands for product, just like sigma stands for sum. product. And you can write, just like you write for a sum, I equals 1 to n. Okay? And the trace of A is the sum of the alpha i's.
Isn't that the definition of the trace?
No. If you take a matrix, its trace is the sum of its diagonal elements. Here I'm saying that its trace is the sum of its eigenvalues.
Which are the diagonal?
That's not A. That's a matrix similar to A.
Okay.
Okay? So why are these true? Why is this a corollary of this theorem? Because suppose A, such A, I mean that all the eigenvalues belong to the field, then A is similar to a matrix that looks like this. Call it B. Okay? It's not A anymore. But similar matrices have the same trace and have the same determinant. So the determinant of this, which is, it's a triangular matrix, the determinant is just the product of the alphas, is the same as the determinant of the original A. That's this statement. The trace of this, which is the sum of all the alphas, the diagonal elements, is the same as the trace of the original A, and therefore it's this. Good? So it's a direct corollary of this theorem, which we didn't prove. Good? Everybody with me? Okay. So the last thing I want to do, again, I know this is a pretty long one, but nevertheless, I want to do an example of how we kind of use these little facts, for example, these, how we use them in order to do very practical things, like, for example, find eigenvalues and eigenvectors and determine diagonalizability. Wow. That's even longer than diagonalizable. Determine diagonalizability without actually calculating the characteristic polynomial and finding its roots, which is something, for example, which is pretty hard to do when it's more than 3 by 3, right? Okay, so let's do an example. I have to find the example first. Ah, there's the example that I wanted to do. So here's an example. Let's look at the matrix. It's going to be a 4 by 4 matrix. The matrix 3, 1, 1, 1, 1, 3, 1, 1, 1, 1, 3, 1, and 1, 1, 1, 3. 4 by 4 matrix. Question. Is A diagonalizable? Okay. Standard way to solve this, right? A minus alpha I, determinant. Calculate that determinant. You'll get a polynomial of degree 4. Hopefully you can set it up such that it's automatically, you can see the roots, and if not, you're in trouble, right? Because finding roots of a polynomial of degree 4 is, okay? And for each, right, we know how to do it. Might be a bit tedious, right? A bit long. Let's do it in a shorter way, okay? So can you guess an eigenvalue? A wise guess, don't just throw, 7 is an eigenvalue. Can you make a wise guess for an eigenvalue here? Wise means based on theorems, for example. Theorems, for example, that were on the board in this lesson.
2 to the power of 4.
Why?
Because if we do row because I'm doing
You lost me a bit.
operations in my head?
No. I don't want you to say, okay, I'm making a guess because I'm already doing the procedure. I'm just not writing it down. Okay? A smart guess, a wise guess without doing any calculations. Just a guess based on a wise observation. Anybody? Okay, so here's a claim. Wise guess. 2 is an eigenvalue. Why? Because what is an eigenvalue? An eigenvalue is something that is a root of the polynomial determinant of a minus alpha I, right? An eigenvalue is an alpha such that when we subtract it from the diagonal, right, we get a matrix with determinant 0. Do you see that if we subtract 2 from the main diagonal, we get a matrix if we subtract, so 2 is an eigenvalue, since if we subtract 2 from the diagonal, we get the matrix 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, whose determinant is what? 0. Why?
Because it doesn't have full rank.
Right. Which has, let's call it, let's call it what it is. We get a minus 2I, which is this, which has determinant of a minus 2I equals 0, obviously, because it doesn't have full rank. That's the theorem. The determinant is 0 if and only if it has full rank, if and only if it's invertible, if and only if, etc. Good? So do you see that? And once you've seen this, once you've seen me guess it once, you're going to start guessing these sort of guesses rather easily in future examples, even when they're 2 by 2 or 3 by 3 or 5 by 5. Okay? Do you agree? Okay? So 2 is an eigenvalue. So we argued this. We found one eigenvalue. How many are we seeking? 4, right? We want to find 4 eigenvalues, maybe up to multiplicity. But I can say even more. I can say even more. What is the multiplicity of 2 as an eigenvalue? What is its geometric multiplicity? Just by looking at this matrix, it's not going to be 4, 3. Okay? So remember, what is the geometric multiplicity? So I'm really bonding together many, many, many little facts that we accumulated. Okay? You have to be very concentrated. Okay? The number of eigenvectors corresponding to the vector, to the eigenvalue 2, is the dimension of the kernel of a minus 2I, which is the same thing as saying the dimension of the null space of a minus 2I. Okay? How many solutions does the system a minus 2I times x equals 0 have?
Infinitely many.
Okay? Infinitely many, but the rank of a minus 2I is 1. That's obvious. I'm not calculating anything. I'm just looking at it. It has rank 1. Do you agree? Yeah. Therefore, the dimension of the null space is 3. Do you agree? So let's write that. The rank of a minus 2I equals 1. There's only one linearly independent row here. All the rest are multiples of it. Therefore, the dimension of the null space, or let's call it, okay, we can call it the null space, but we're thinking of the kernel right now. is 3, right? They need to add up to 4. That's the rank nullity theorem, right? So this means that alpha equals 2 has 3 linearly independent eigenvectors corresponding to it. We're going to have 3 degrees of freedom. We can construct 3 linearly independent eigenvectors corresponding to 2. So alpha equals 2 has geometric multiplicity three. Do you agree? Okay. You have to, we're really using a lot of stuff now, right? If it's, whoa, you have to press pause and think on each statement that I just made. Okay, everybody good? Okay. So alpha equals 2 has geometric multiplicity 3, right? If A is going to be diagonalizable, if it's going to have a diagonal form, right, then if we can show that the algebraic multiplicity of alpha equals 2 is 3, then we're done, right? Because then alpha equals 2 has the same geometric and algebraic multiplicity. And there's going to be one more alpha, some other alpha. I don't know what it is, but that it's going to have only one for both, right? And therefore, for each one, the geometric and the algebraic multiplicities agree, and we're done. Do you agree? So what could be, at this point, the algebraic multiplicity of 2? We already know that the geometric multiplicity is 3.
1, 2, 3.
No.
3 and up.
3 or 4. Okay, the geometric multiplicity is always less than or equal the algebraic multiplicity. That was a theorem last time. Remember? So the algebraic multiplicity of alpha equals 2 is either 3 or 4. If it's 4, that's it. A is not invertible, not diagonalizable. If it's 3, that's it. It is. Do you agree? We're almost there. So let's write that. And note, I'm not calculating at any point, really calculating the characteristic polynomial or doing any of the long procedure. And in fact, this is taking me a few minutes because I'm explaining everything. But if you already get the hang of it, you do these sort of ideas and arguments, you really do them quickly. Okay? So continuing. So alpha equals 2 has algebraic multiplicity 3 or 4. Right? Because its geometric is 3, and the algebraic is greater than or equal to that. Okay, so it's 3 or 4. What are all the eigenvalues of A? All eigenvalues of A are, the first one is 2, the second one is 2, the third one is 2, alpha has multiplicity at least 3, and then there's another one, which I don't know yet. It can either be also 2, in which case it would have multiplicity 4, or it can be something else. Do you agree? So those are the 4 eigenvalues of A. Okay? But I know one thing about them. Let's go back to the previous corollary. The trace of A is the sum of the eigenvalues. Remember this? The trace is the sum. Let's go back to the matrix. Did you follow me to that board? Okay, just making sure. The trace of A is the sum of the eigenvalues. Now I'm going back to this board. The trace of A is 12. Do you agree? Okay. So back here, the trace of A equals 12, and therefore A must have 6 here. 6 as the fourth eigenvalue. 6. A must have alpha equals 6, or alpha 2. Let's call this alpha 1. Alpha 1 equals 2 has multiple. A must have alpha 2 equals 6 as an eigenvalue. Okay, so this mystery box has to be a 6, because the sum of these guys has to be, the trace has to be 12. Do you agree? And that settles it. Alpha 1 equals 2. So conclusion, alpha, geometric multiplicity, GM, algebraic multiplicity, AM, alpha equals 2 has geometric multiplicity 3 and algebraic multiplicity 3. Do you agree? And alpha equals 6 has geometric multiplicity 1 and algebraic multiplicity 1. If it's 1, it's going to be 1 in both, right? If this is 1, this is less than or equal to it. It can't be 0, right? It's an eigenvalue means it has at least one eigenvector. So that's it. So for any two, sorry, for all eigenvalues of A, the geometric and the algebraic multiplicities coincide, and therefore A is invertible. This was very, very long, I know. Not invertible, thank you. Diagonalizable. Okay, I know it's been very long, but I wanted to kind of collect all these ideas. And you're probably going to see many more examples of this sort. But remember that it's always wise, when you get such examples, to take a step back, and before you implement the standard machinery of calculating the characteristic polynomial and finding the roots and so on and so forth, it's always good to try making these shortcuts, to try, okay? Sometimes they work, sometimes they don't. Sometimes, so for example, here we already know the diagonal form, right? The diagonal form is going to be 2, 2, 2, 6, right? But we don't know the eigenvectors, right? If somebody asks us for P, we still have to go back and do the standard routine. So the shortcuts are only good for some of the stuff. Good? Okay, so we'll stop this one here. We still have a few more things to say before we move on to our next and last topic, but we'll do that in a separate clip.